I'd like to welcome you all here for this evening in our annual Jansky Lecture. The Karl G. Jansky Lectureship is an honour established by the trustees of Associated Universities Incorporated to recognise outstanding contributions to the advancement of radio astronomy. First awarded in 1966, it is named in honour of the engineer who, in 1932, first detected radio waves from a cosmic source. Karl Jansky's pioneering discovery of radio waves from the central region of our Milky Way galaxy started the science of radio astronomy that we continue in many different ways today. We are very honoured this year to have a lot of the Jansky family with us here, and Ken will actually introduce them all a little later. We had a lovely dinner with the Janskys. This is the largest collection of Janskys in 40 years, I was told. And we had a lovely dinner, and after the police came and took some of them away last night, we realised that this is a special honour to have the family of Karl with us for this lecture. The NRAO, Greenbank Observatory and AUI are pleased to award the 2024 Karl G. Jansky Lectureship to Dr. Ken Kellermann, Senior Scientist Emeritus of the National Radio Astronomy Observatory. Dr. Kellermann earned his PhD in Physics and Astronomy at the California Institute of Technology under John Bolton in 1963, studying the radio spectra of galactic and extragalactic radio sources. He joined the NRAO in 1965 and has served many roles, acting Assistant Director for Greenbank Operations, as Chief Scientist, and as head of its New Initiatives Office. Dr. Kellermann's studies of radio galaxies, quasars, and cosmology cover more than half a century of research. His collaborations with scientists and radio telescope facilities around the world in the development of very long baseline interferometry resulted in the construction of NRAO's Very Long Baseline Array in 1993. Among his many accolades, Dr. Kellermann won the Helen B. Warner Prize for Astronomy from the American Astronomical Society in 1971, the Benjamin Gould Prize of the National Academy of Sciences, and the Bruce Medal of the Astronomical Society of the Pacific in 2014. He is a member of the AAS, IAU, ERSI, the US National Academy of Sciences, the American Philosophical Society, a foreign member of the Russian Academy of Sciences, and an external member of the Max Planck Institute for Radio Astronomy. Dr. Kellermann is the co-author of Open Skies, the National Radio Astronomy Observatory and its impact on US radio astronomy, together with Ellen Bouton and Sierra Brandt. More recently, his book with Ellen Bouton, Star Noise, Discovering the Radio Universe, tells the fascinating story of the remarkable, mostly accidental, and serendipitous discoveries in radio astronomy that have transformed our view of the universe. Much like the participants he described so well in these books, Dr. Kellermann has played a huge role in the incredible history of our scientific endeavour, inspiring generations around the world and at our observatory. Tonight, Dr. Kellermann will deliver his lecture, Discovering the Radio Universe. Please join me in congratulating Ken as our 2024 Jansky Lecturer.
Well, thank you, Tony. Thank you very much for the kind introduction. And I'm very grateful for being chosen as the Jansky Lecturer this year. I've been in NRAO for nearly all of my professional career, and I can't imagine to have had a better place to have worked. And so I'd like to take this opportunity to thank NRAO and AUI for providing me with a home, and all of my colleagues, past and present, for putting up with me now for more than half a century. I think I've been, during this time, to almost every one of the previous Jansky lectures, starting with the one that Tony mentioned, John Bolton, back in 1966. Bolton was my PhD supervisor at Caltech, and he was the one that got me started in radio astronomy. But it sort of happened by accident. I only became a radio astronomer because I misunderstood one of the questions that he was asking me during a very brief interview, and I accidentally gave him the answer They got me the job. Now, I didn't go to Caltech planning to study astronomy. In fact, I had no idea that one could have a career as an astronomer. I think it was something you read about in books or something. I was actually planning to study physics. And I had an assistantship for which required that I work for some faculty member for 15 hours a week, for which I'd get paid $1,800 a year. That's graduate students, that's $1,800, not $18,000 a year, not per month. And I was given 2 weeks to find something that was interesting to me, and also a professor that was willing to take me on. I went around, talked to various faculty members, and everyone I spoke with was very polite and cordial. They took the time to explain their research. I talked to people working in nuclear physics, atomic physics, low temperature physics, solid state physics. And they asked me a lot of questions about the courses I had taken, my grades, especially in math. I didn't really find anything that interested me. And I think, frankly, I don't think they were interested in me either. Well, when my 2 weeks were running out, the head of the physics department suggested that I might go over and talk to Professor Bolton, who was starting this new project in radio astronomy. And that sounded like it might be interesting. So I went over to the astronomy building and found Bolton's office, and the secretary is sitting there. And I said, I'd like to see Dr. Bolton. And she glared at me and said, "That's Mr. Bolton over there." And Bolton turns around. I said, everybody else had been polite, and Bolton turns around and says, he looks at me and says, "What do you want?" And I clearly interrupted whatever it was he was doing. And I was confused. It's Mr., Doctor, Professor of Business. And I'm thinking, this is Caltech, not Podunk U, and how can a Caltech professor not have a PhD? So I was so confused, I just mumbled something about, well, maybe I might be interested. I wanted to find out about radio astronomy or something. And then he just asked me two questions. He wasn't interested in what courses I had taken or whether I could solve partial differential equations, but he asked me what I knew about electronics. And I told him I was a radio amateur, and I could read circuit diagrams, I knew how to use a soldering iron, I could build equipment and so on. That was a good answer. He liked that. But then he asked the key question, which I completely misunderstood. And because I misunderstood what he was asking me, I gave him the answer that he was looking for. He asked me how I felt about heights. Well, I knew the observatory he was building was at 4,000 feet elevation in the Owens Valley, and I had spent the previous summer with a high school friend traveling around the country. We were camping in the Sierras and the Rockies, hiking at 10, 12, even 14,000 feet. So I just said, "Oh, heights doesn't bother me at all." That's not what he meant about heights. And if he had known, I think that, I'm actually kind of scared of heights, that would have been the end rather than the beginning of my career in radio astronomy. And there was no further discussion. He just told me, "Okay, you can take that, there's an empty desk in the office next door." And I'm thinking, no, wait a minute, I just came to ask, to find out a little bit about radio astronomy. I need to think this over. And I'm also thinking to myself, I'm not sure I really want to work for this guy. But then I realized my 2 weeks were almost up, and I had to do something to earn my $1,800. So I figured, okay, I'll do this radio astronomy thing for the first semester, and that'll give me time to find something better. Well, that was 65 years ago. and the past 65 years has really been a fantastic time for radio astronomy. Most of the cosmic phenomena that we study today is studied by astronomers, and even see on television and read about in the newspapers. It was all unknown back then. Things like quasars, pulsars, the cosmic background radiation, interstellar masers, gravitational lenses, black holes, dark matter, and lots of other things were all discovered since I began to work in radio astronomy. Now, unfortunately, or at least unfortunately for me, I had nothing to do with any of these discoveries, but I did get to know most of the major players the scientists who made these discoveries and were later able to share their experiences with me. Most of these discoveries were accidental or serendipitous. The scientists involved were mostly looking for something else, or in many cases, they had a new instrument and were just looking. And they accidentally discovered something new. Generally, theory played no role in these discoveries, and in some cases, incorrect theory even pointed in the wrong direction and actually delayed the discovery. Mostly the men and the women involved were very young, generally in their 20s and 30s, and some were still graduate students when they made their big discovery. Most of these discoveries were the result of using a new technology or new techniques, things like interferometry and aperture synthesis, large, precise radio telescopes, and of course the development of very sensitive receivers were all critical in bringing about these new astronomical discoveries. In 1972, I had an undergraduate student named Stephen Chu, and Chu went on to win a Nobel Prize for using lasers to cool and trap atoms, and he later became Secretary of Energy under President Obama. I can't even pretend to understand what he did and why he got his Nobel Prize, so I can't claim any credit for training him, except to think that perhaps he may have been influenced by what he saw happening at NRAO in radio astronomy, and which led him to later write, "If you're the first person to look under a rock with a new set of tools, you don't even have to be that smart to discover something new." And indeed, I think, as I said, it's been to a large extent that it's been these new tools that's driven the history of radio astronomy. Although I think the people involved who made these discoveries, they were actually pretty smart themselves. But they were mostly engineers and physicists. There were very few astronomers, and in many cases, like John Bolton, they had only minimal academic training. As you might expect, a lot of these discoveries were made in university laboratories or observatories, but some of it came from work that was done in industrial or even military laboratories. And then, of course, there was Grote Reber. Reber didn't have any institutional affiliation, and he used his own personal funds to build the world's first radio telescope, essentially in his own backyard. I never met Karl Jansky. He sadly died while I was still in middle school, but it's been a real honor to get to know his family, including his late wife, Alice, Karl's son and daughter, David and Anne Moreau, who are both here. Please stand up. And also his grandchildren, Gregory, Christopher, Carla. And also one of Karl's many nieces, Mary Ann. Thank you, thank you. Thank you all very much for coming tonight. We're truly honored. Now, Karl Jansky didn't set out, of course, to discover cosmic radio emission. He was actually working for the telephone company, and of course, back in the 1930s, there weren't any undersea cables or satellites, and AT&T was using shortwave radio for the transatlantic phone connections. And Jansky's job was to find out what was causing interference to these radio links. And in order to find the source of interference, Jansky built this directional antenna, which operated at 15-meter wavelength. And in several ways, he was very lucky to have been able to discover cosmic radio noise with this antenna. If it had been working at a longer wavelength, then the galactic radio noise would have surely been blocked by the Earth's ionosphere. If he had worked at a shorter wavelength, then the galactic radio noise would have been too weak to have been observed with his relatively primitive equipment. Also, Jansky was working near the minimum of the 11-year sunspot cycle. If he had done his work a few years earlier or a few years later, when the sun was more active, as it is these days, the ionosphere would have blocked the cosmic radiation, even at 15 meters. Karl's antenna spun around every 20 minutes, 3 times an hour. His kids, who are here, well, they're not kids anymore, played on it, called it their merry-go-round. And the radio noise was recorded on these long rolls of chart paper. And it was during the winter of 1931, 1932, that he noticed that the maximum noise he was getting came when his antenna was pointed toward the sun. That is, you see, 3 times an hour, the noise peaks up when the antenna was looking at the sun. Now, Jansky had no background in astronomy, and he didn't appreciate that in the wintertime, the sun just happens to be in the same direction in the sky as the center of the Milky Way. Now, Jansky's father was a professor of electrical engineering, and Karl regularly wrote to him and kept him informed about his work. And so he wrote to his father, it always comes from a direction that's the same or nearly the same as the direction the sun is from the antenna. And this was an important discovery, but then it seems that he was distracted by other telephone company work, and he actually wasn't able to have the time to go back and look at his data until nearly a year later. And by then he realized, of course, that the sun had moved away from where the radio noise was coming from. And he wrote to his father that the noise comes not from the sun, but from a direction fixed in space. And I think it's very interesting. And I mean, it really was interesting. Radio noise coming from the Milky Way. And remember, this is 1933. Space and astronomy and so on weren't the same household words that they are today. And Jansky suddenly, he became very famous. His story was carried in newspapers around the world. He was on the front page of the New York Times. He was in Time magazine. He was invited to give talks at professional meetings. He was interviewed on a national radio broadcast, which actually carried what he called star noise directly from Bell Labs to the radio transmitter in New York. And it seems everybody was excited about Jansky's discovery from the radio noise from the Milky Way, except apparently the people at Bell Labs. But we have to remember, this is 1933. It was during the Depression. Bell Labs had recently had a layoff. Employees were down to a 4-day work week. And galactic radio waves doesn't really help build telephones. And Jansky spent most of the rest of his career working on telephone company business and then later on defense-related electronics. And for nearly the following decade, Grote Reber was the only person in the world who seriously followed up on Jansky's discovery. And in the summer of 1937, he took off from his job as an engineer and built this 32-foot dish in his backyard in Wheaton, Illinois. As I said, it was the world's first radio telescope, and he was only 25 years old at the time. He was a good scientist, and he understood that if the galactic radio noise that Jansky had discovered came from a hot interstellar gas, that the intensity should increase as the square of the observing frequency. And so he designed his equipment to work at the highest possible frequency that was then feasible, 3,300 megahertz. But he was surprised and disappointed that he didn't detect anything. And so he redesigned the receiver to work at a lower frequency, 910 megahertz. And still he didn't detect anything. So he rebuilt it again for 160 megahertz and finally detected Jansky's galactic radio noise, but it was about 100 times weaker than predicted. And Reber realized that Jansky's star noise could not be the kind of familiar thermal noise that increases with frequency, but that Jansky had discovered a new phenomena, what we now call non-thermal radiation, where the intensity decreases with increasing frequency. And then Reber spent the next few years making the first detailed maps of this non-thermal radio noise from the Milky Way. He still had his regular daytime job as an engineer. He came home after work. He had an hour commute between Chicago and Wheaton, an hour each way. I was there a few years ago and took the train, and it still takes an hour each way to go back and forth. But he came home, had dinner, observed until midnight or 2 a.m., got a few hours sleep, went back to work, and on weekends he analyzed his data and made these maps. But by the late 1940s, Reber realized that he was really no longer able to compete with the new well-funded university and government radio astronomy projects, so he decided to sell all of his equipment to the U.S. government, and he went to work for the National Bureau of Standards. Now, Reber's original antenna is now located at the entrance to the Green Bank Observatory in West Virginia. And the picture on the right was taken about 30 years ago during one of Reber's many visits to Green Bank when he decided he needed to repair his antenna. And he drafted me to help, I don't know, hold his tools or something. But as part of his sales pitch, when he was demonstrating his telescope to representatives from the Bureau of Standards, his chart recorder just went off scale, and at the same time, people could hear a loud crackling noise coming from his receiver. And what had happened was that he had accidentally discovered very powerful radio waves coming from the sun that were the sun was so strong that they were coming into the side lobes of his antenna, even when the antenna wasn't pointed at the sun. And to claim credit for his discovery, he quickly dashed off a paper, I think the same day, to Nature magazine. Well, it turned out that this wasn't really the first time anyone had detected the radio noise from the sun. Back in 1942, Britain was being attacked daily by German aircraft, and they were expecting a full-scale German invasion, and England built this chain of radar stations along the south coast of Britain. On February 12th, 1942, this German battleship, the Scharnhorst, along with several other warships, somehow managed to sail up the English Channel, and they were able to get safely back to their home port in Germany. And it was because of apparently strong interference to the British radar that they just went undetected. And this caused a great panic, not only in England, but even in the US. I mean, everyone was concerned. Germany had apparently devised some sort of jamming technology that made the radar defenses essentially ineffective. There was a parliamentary inquiry and calls for Winston Churchill to resign as prime minister. And it looked like a dangerous turning point in the war. Now, J. Stanley Hay was a civilian working for the British Air Force, and he was instructed to find out more about this German radar jamming, which he noticed curiously seemed to continue even when there were no airplanes or ship movements. And he became even more suspicious when he realized that the apparent jamming occurred only in the daytime. And he contacted the Royal Observatory, and he learned that on February 12th, indeed, there had been intense solar activity. A new giant sunspot had appeared, and he correctly concluded that the apparent, what they thought was radio jamming, was coming not from Germany, but was coming from the sun, and was associated with this new sunspot. And Hay described his discovery in a very detailed report, but remember, this was wartime, and his report was classified, and it remained a secret until 1946. And we now know that later during the war, many other radar operators, both on the Allied side and the German side, apparently independently detected radio noise from the sun, but it was all kept secret. And so Grote Reber had the dubious honor of having the first publication reporting strong radio bursts from the sun. And after the war, Hay went on to make his own maps of the galactic radio noise, and he accidentally discovered one very localized region in the sky where there was very strong radio emission from a very small region. And this was called, this is the first of the so-called discrete radio sources. It was called Cygnus A because it's the brightest radio source in the constellation of Cygnus. But there was no obvious counterpart to this very strong radio source. And shortly after that, John Bolton and Gordon Stanley in Australia discovered three other sources of strong radio emission. One of these radio sources lay in the direction of the Crab Nebula, which is well known to astronomers as the remains of a supernova that exploded in the year 1054. The Crab Nebula is very far away, and Bolton calculated it had to be an incredibly strong and powerful radio source. They also found two other radio sources that were in the same direction as two bright galaxies. One, known as NGC 5128, had this well-known dust lane crossing the galaxy, and the other, M87, has a jet which extends far away from a bright nucleus. And Bolton realized that if M87 and NG5128 were really galaxies, they'd be 1,000 times further away than the Crab Nebula. And this meant that they'd be more than 1,000,000 times stronger than the Crab Nebula. And apparently, he just couldn't comprehend that anything could be that strong a source of radio emission. And he argued that M87 and NG5128 were not really distant galaxies, but they must be just gaseous nebulae in our own Milky Way. And so they were really only as luminous as the Crab Nebula. Nevertheless, their publication with this innocuous title, Positions of Three Discrete Radio Sources of Galactic Radio Frequency Radiation, is now recognized by historians as the discovery of what we now call radio galaxies. And soon after that, other astronomers identified the Cygnus A source with a very faint and rather distant galaxy. And since Cygnus A is the strongest radio source in the sky, this suggested that the weaker radio sources were likely to be even further away and were probably actually far beyond the limits of even the biggest optical telescopes. And I think for the first time, this generated a lot of new interest in radio astronomy. I think, which had previously been ignored by, I guess, what I call the real astronomers. And the hunt was on to find more distant radio galaxies. It was naturally assumed that the further away they are, the smaller they would appear. And so everyone concentrated on observing small radio sources. And it was around this time that John Bolton moved to Caltech and started the new radio astronomy project there. And one of his goals was indeed to find smaller and presumably more distant galaxies. Everyone was trying to find the most distant objects in the universe. And Bolton and his colleagues were very successful. Actually, it was Bolton and a lot of his students, one of whom is here tonight, Ed Formelant, who made some of the measurements. But then there was an apparent setback. The radio source known as 3C48 looked like when photographed optically, it looked like a nearby star, not a galaxy. And using the 200-inch telescope, Alan Sandage discovered that 3C48 was variable. That is, it changed brightness from hour to hour. Just typical of many stars, but certainly not a galaxy. And 3C48 had a very unusual optical spectrum with very strange emission lines that nobody could recognize. Jesse Greenstein was a professor at Caltech and an expert in optical spectroscopy. And he spent several years trying to understand the spectrum of 3C48. And meanwhile, John Bolton, who had no training in spectroscopy, thought he could interpret the spectrum if one just assumed that the lines were just shifted by 37%, which meant that it would be a distant galaxy and wasn't really just a star. However, Greenstein just rejected Bolton's speculations, essentially told him, you're just a radio astronomer, you don't understand this stuff. And Greenstein instead went ahead and interpreted the spectrum in terms of highly exotic ionized rare earth elements, and he submitted a very lengthy paper for publication in the Astrophysical Journal. And he went around and handed out preprints to all the other Caltech professors. I was only a graduate student at the time, so I didn't merit getting a preprint from him, but I did manage to get an unauthorized copy from one of the other faculty members. And the breakthrough came a few years later when the strong radio source 3C273 was occulted by the moon. So this is when the moon passes in front of the radio source in the same way you have an eclipse of the sun when the moon passes in front of the sun. And since we know the position of the moon very accurately, by timing when the moon occults the radio source, we can determine its accurate position in the sky. Astronomers hadn't previously shown much interest in the radio source 3273 since it wasn't very small, and they thought it was a relatively nearby galaxy, and they sort of ignored it, even though it's one of the brightest radio sources in the sky. Now, by this time, Bolton had moved back to Australia, where he was now in charge of the new Parkes radio telescope. And then he, with colleagues, used the occultation to determine a very precise position of 3C273. They thought it was accurate to about a second of arc, but they made a simple mistake in calculating the position of the moon, and so their position was actually in error by 15 seconds of arc. And Bolton then sent these incorrect coordinates to Martin Schmidt at Caltech. And of course, that confused Schmidt. The optical image of 3C273 appeared to show both this bright star and a faint nebulosity. The position that Bolton had sent was off somewhere else. It didn't coincide with either of these objects. Schmidt assumed that it was the nebulosity that was a faint, distant galaxy, and that it was probably the radio source, and that the star was just a random bright star in the field. But like 3C48, the star had a very unusual pattern of emission lines. It somehow looked familiar to Schmidt, but somehow didn't seem quite right. And he puzzled over the spectrum for about 6 weeks until he realized that the lines in 3C273 were the familiar hydrogen lines, but they were shifted in wavelength by about 15%. So this meant that although 3C273 looked like a star, it was actually located in a relatively distant galaxy. And armed with this new understanding of the spectra, Schmidt and Greenstein then went back to re-examine the spectrum of 3C48, which they then realized had an even larger redshift, 37%, which is just the value that Bolton had argued for 2 years earlier and Greenstein had just rejected. And for the lack of any other name, Schmidt called these objects quasi-stellar radio sources because they looked like stars but weren't stars. And that later got shortened to quasars. And after he realized that the 3C48 wasn't a star and that his paper was all wrong, Greenstein withdrew his paper from the Astrophysical Journal, and he confiscated all the preprints that he had distributed. But he didn't know about mine, and so he didn't get mine. And I think for a while, until I made copies for others, I had the only remaining copy of what would have been a very embarrassing paper. Now, we now recognize that quasars are very distant, and they're among the most energetic objects in the universe. As it later turned out, both 3C273 and 3C48 and many other quasars had been previously photographed many times by astronomers, going back as far as 1880. But they were thought to be just ordinary stars in our own Milky Way, and so they had been pretty much ignored. And since quasars are so bright, Schmidt's discovery initiated a whole new furious hunt to find the most distant objects in the universe. Tony Hewish was a radio astronomer in Cambridge, in England. Margaret Clark was one of his PhD students, so he assigned Margaret the task of finding new compact radio sources that might be distant quasars. But Margaret became puzzled when one of her very small radio sources seemed to vary, but in a different way than it seemed to vary erratically. And Hewish, who was an expert on the sun, immediately recognized that this was probably due to the solar wind passing in front of the radio source, in the same way that stars twinkle due to irregularities in the Earth's atmosphere. The existence of a solar wind had actually been predicted much earlier, but had never been observed until Margaret Clark accidentally discovered the solar wind when she was looking for new quasars. Well, Hewish got excited again. Here was an opportunity for the first time to observe the solar wind directly, and he built a new antenna. Well, he actually didn't build it. He used the time-honored tradition of having the graduate students do the heavy work of building the array. And one of his students was Jocelyn Bell. And when the array was finished, Jocelyn's job was to analyze the data, which came out on these rolls of chart paper. She had to look at 100 feet of records every day, and she found one very peculiar radio source that was varying, but instead of varying in the random way that Margaret Clark's source had varied, Jocelyn's source appeared to pulse once every 1.3 seconds. And she recognized, this is pretty unusual. Nobody had ever discovered anything like this, and she reported her discovery to her supervisor. And Hewish was an experienced radio astronomer, and he thought he knew that there can't possibly be anything in the sky that does that. And so he told Jocelyn that she was seeing man-made interference, and she could get back to her work on the solar wind. But Jocelyn had already determined that this peculiar periodic radio source lay in a direction that was fixed in space, not fixed in a direction on the Earth. And so she said that she told Hewish, well, it may be man-made, but it's not from an Earthman. And this led to speculation that it might be an interstellar beacon that extraterrestrials were using to navigate around the galaxy. And somewhat whimsically, she labeled her radio source LGM1, standing for Little Green Men. Now, we now know, of course, that these periodic radio bursts come from pulsars, which are very rapidly rotating, very highly magnetized stars made up of only neutrons that pack very close together. So the whole star is only about 10 miles in diameter, and the neutron star spins around. There's a beam of radiation, and every time it comes around and points toward the Earth, you see a pulse, just like a lighthouse. The existence of neutron stars was actually predicted back in the 1930s, but they were discovered only accidentally by Jocelyn Bell while she was looking for something else, the solar wind, which in turn was discovered by Margaret Clark when she was looking for more quasars. Apparently, the word pulsar was found on a blackboard in Cambridge after some press conference. Nobody seems to know who actually came up with this name, but it stuck through the years. 7 years later, Hewish shared the 1974 Nobel Prize in Physics for his role in the discovery of pulsars. As it later turned out, during the time of the Cambridge work, the United States was operating a so-called ballistic missile early warning system. This is a chain of radar stations stretching across the North Atlantic from Alaska through across Canada to Greenland. And the idea was that this would give advance warning of Russian missiles coming over the North Pole headed toward the US. But in 1967, Charles Schleicher was the operator in charge of one of these radar stations that was located near Fairbanks, Alaska. And he noticed that he was receiving radar echoes even when he wasn't transmitting, which is kind of strange. He had been a navigator on a B-47 bomber, and so he knew something about celestial navigation, and he worked out the position in the sky where these pulses were coming from, and he realized they were coming from the Crab Nebula, fortunately not from Russian missiles. And he then went on to locate a number of other pulsars, and it was all pretty interesting. He recognized the scientific importance of his discovery. It was 1967, it was during the Cold War, and Schleicher's discovery was classified and wasn't made public until nearly 40 years later, decades after Jocelyn's discovery and Hewish's Nobel Prize. A lot of pulsars are pretty strong radio sources, and the only reason that think that they hadn't been discovered earlier by radio telescopes is because radio telescopes weren't designed to detect pulse radiation. Radar systems are designed to detect pulse radiation, and probably there were many pulsars or many radar facilities that had previously detected pulsars, but of course didn't recognize what they were. And the discovery of pulsars was really important. It's led to a number of other important discoveries. For example, Russell Hulse was still a graduate student working with Joe Taylor, and he was observing at Arecibo when he discovered what's called a double pulsar. This is a pulsar that was in orbit around another neutron star, and working with this Joe Taylor, they showed that the pulsar orbit was gradually changing as it was losing energy due to gravitational radiation. Now, the existence of gravitational radiation was predicted by Einstein back in 1916, but he thought it would be so weak that it couldn't possibly ever be observed. And Hulse and Taylor shared the 1993 Nobel Prize in Physics for their discovery of the double pulsar and gravitational radiation. Also in 1991, Alex Vogtson, he was also using the Arecibo telescope to observe pulsars. And at the time, the antenna was being repaired, so it couldn't be steered around the sky, and Vogtson could only observe in a very narrow strip of sky that just happened to pass overhead. And one of the pulsars that just fortunately lay in this small strip of sky, he saw behave strangely. Normally, pulsars are very precise clocks, accurate to a microsecond per year. But this one had curious variations in the pulse period. And after Dale Frail used the VLA to further study the pulsar, they realized that the timing anomalies were caused by at least two planets that were circling the pulsar, orbiting the pulsar, and the planets each produced a small tug on the pulsar position, and this led to the timing irregularities. This was the very first discovery of any planet that was located outside of our solar system. And it turned out that both planets had masses that were comparable to or a few times greater than the mass of the Earth. And it would be another 2 decades before any other Earth-like planets were discovered. Well, I think one of the most important astronomical events of the 20th century was the discovery of the 3-degree microwave background, which was discovered by Arno Penzias and Bob Wilson at Bell Labs. The cosmic background radiation is a weak radio glow coming from the whole sky that's left over from the original Big Bang at the start of the universe that presumably happened some 14 billion years ago. Now, Penzias and Wilson didn't set out to discover the beginning of the universe. Like Jansky, they were working at Bell Labs for the telephone company. And in fact, their antenna was located very near the same site where Jansky had built his antenna. And Penzias and Wilson were using this very sophisticated 20-foot horn reflector that was originally designed by Bell Labs to be used on telephone relay towers. And Penzias and Wilson built what they thought was a very sensitive receiver, but they were discouraged when they found that there was more noise coming from their receiver than they expected, and they assumed they had made some sort of it was due to some sort of subtle instrumental effect. And while they were still trying to figure this out, Penzias accidentally became aware of an experiment that was going on at nearby Princeton University that was actually, in fact, intended to detect this faint radio signal that might be left over from the Big Bang. And after talking with the Princeton group, Penzias and Wilson realized that they had actually accidentally discovered the faint radio noise that signaled the beginning of the universe. They published they didn't publish a paper, actually. It was a very short note, just 1 page in the Astrophysical Journal that was almost entirely technical. They made no mention of any cosmological implications, except they had a 1-sentence reference to a possible explanation, a quote, possible explanation that was contained in a separate paper that was published by the Princeton group. Their 1-page note became one of the most highly cited papers in astronomy in the latter half of the 20th century. It's been referred to more than 1,500 times in subsequent publications. It literally started a whole new field of cosmology. Hundreds, if not thousands, of scientists later became involved in studying the cosmic background radiation. It's also generated the construction of dozens of new telescopes, all intended to study the cosmic microwave background, which was accidentally discovered by Penzias and Wilson while they were testing out their new receiver. It later turned out that there were many other scientists who had previously detected the cosmic background emission, but they had either ignored it or swept it under the rug as an unexplained instrumental effect, or in several cases, they just didn't recognize its importance. And Penzias and Wilson won the 1978 Nobel Prize in Physics for their discovery of the cosmic microwave background radiation. Now, I've mentioned a number of Nobel Prizes won by radio astronomers. Actually, there is no Nobel Prize for astronomy. The legend has it this is because Nobel's wife ran off with an astronomer. In fact, there's no evidence that Nobel was ever even married, but I mean, it makes a good story. But for whatever the reason, until 1974, no one was ever recognized with a Nobel Prize for any work done in any field of astronomy. And then, interestingly, the first 6 scientists to receive a Nobel Prize for astronomical discoveries were all to radio astronomers. And by 2006, there were another 2. So now there's a total of 8 radio astronomers who've been recognized with Nobel Prizes. Jansky himself was nominated in 1948, but I think this was before the impact of his discovery was really widely appreciated. And Jansky died in 1950 when he was only 44 years old, and was no longer eligible. And I'm sure had he lived longer, surely he would have been recognized by a Nobel Prize for his discovery of cosmic radio noise. Now, as I indicated at the start, there are many other discoveries by radio astronomers I haven't had time to discuss. These include electrical storms on Jupiter, interstellar molecules, cosmic masers, apparent faster-than-light motion in quasars, gravitational lenses, and many other things. So why were radio astronomers the first to make all the discoveries of phenomena that had been previously unknown? Well, remember, astronomy is an observational science. Astronomers can't do experiments. All we can do is look. And way back in 1609, Galileo used a telescope for the first time to study astronomical bodies. And he discovered the moons of Jupiter, the phases of Venus, and the rings of Saturn. And for the next 300 years, astronomers built bigger and better telescopes and made more discoveries. But they were all confined to this narrow slice of the electromagnetic spectrum that we know is visible light. Now, all that changed with Karl Jansky's discovery of radio noise from the Milky Way. For the first time, astronomers could look outside the traditional optical window. Now, of course, more recently, we have orbiting observatories which have opened up other parts of the electromagnetic spectrum, X-rays, gamma rays, infrared, ultraviolet, which are all blocked by the Earth's atmosphere, but they're all now part of everyday astronomy and observed from satellites. But it was radio astronomy that was the first to reach out beyond the visible spectrum, and so I think it isn't surprising that it was radio astronomers who were the first to uncover all these previously unknown phenomena. Now, I've plotted here the number of radio astronomy discoveries as a function of time. As you can see, it started out slowly with Jansky and Reber, and then the number of discoveries rapidly rose during the 1960s and 1970s, maybe even to the 1980s, but then leveled off, and there have only been a few new discoveries made during the past 40 years. Very, very different from the first 40 years. So what's happened? Well, maybe by 1985 we had discovered everything, and there was nothing left to discover. I think that's probably not right. I mean, going back to when cosmology was an elephant standing on the back of 4 turtles, man thought he understood the universe, but in fact, man has never understood the universe, and there's no reason to believe that at this point in time anything is different, and we know it all. Maybe the explanation is we run out of new technologies, or maybe our instruments are just getting too big and too expensive to afford. Also, the data from modern radio telescopes are so extensive and sophisticated that the scientist doesn't get to see the data until after it's been partially digested by a computer. And as Jocelyn Bell wrote in her thesis, if the aerial output had been digitized and fed directly to a computer, pulsars might well not have been discovered because the computer would not have been programmed to search for unexpected objects. I guess pretty soon we'll be using artificial intelligence to analyze the data, and maybe this will lead to new discoveries, but maybe it'll hinder new discoveries. I'm not sure which. And also, over the last half century or so, the sociology of science has changed a lot. In the pioneering days of radio astronomy, a single individual, or perhaps a small group of 2 or 3 people, could conceive of a program, design and build the equipment, carry out the observations, and then interpret the data. They understood every aspect of what they were doing, and they were hopefully able to distinguish between subtle instrumental effects and genuine new discoveries. Today we have teams of highly skilled engineers who design and build the equipment, but they don't use it. And there are also equally skilled astronomers who use the equipment, but don't build them, and so they may not fully understand their limitations. And also, I think some of our instruments now are so complex that there's no single individual who really fully understands the whole instrument and its limitations. Another change is peer review. Now, of course, it had been traditional in the scientific community for scientific journals to have papers reviewed by outside experts before publication. And the idea was to be sure that no nonsense gets published. But now the competition to use our large telescopes is so intense, and there's typically more proposals to use a facility than there is available time. And so proposals to use large telescopes are now evaluated by a similar peer review process. In other words, in order to get to use a telescope, other astronomers get to tell us what we can and cannot study. And to exacerbate the problem, it's very expensive to build and operate large radio telescopes, or all telescopes. So there's a lot of pressure to produce results. And therefore, the peer review process tends to be very conservative and avoids taking risks that might have really discovered something new. So this means that in order to get permission to use a telescope, and now even to get a job or a research grant, scientists are asked to describe their expected results in such detail that if known so well in advance that what they were going to learn, that the proposal itself, investigation itself might not even be necessary. In other words, if you have a brilliant idea and you want to do something, you first have to convince others who are perhaps less brilliant, or maybe just less innovative, and they also may be your competitors. So imagine if Grote Reber had to ask the NSF or the government for money to build the world's first radio telescope. Tommy Gold was a well-known astrophysicist and was also known as a very outspoken scientist. And he liked to compare astronomers to sheep. And he pointed out that unless one followed the herd, they might be ridiculed or ignored. And so he argued that there's a lot of pressure for scientists to follow the herd, and especially young scientists who are trying to make their career. And he pointed out that following the herd may be a good tactic for advancing one's scientific career, but probably not good for the progress of science. Now, in 2002, former Secretary of Defense Donald Rumsfeld gave a press conference, and he was asked about weapons of mass destruction. Oh, sorry, you went too fast. He said there are things that we know we know. These are the known knowns. We also know that there are known unknowns. That is to say, there are some things we know we do not know. And there are also unknown unknowns, the ones we don't know we don't know. So what's this got to do with radio astronomy? Well, the known knowns are the things that I've been talking about for the last hour, the things we think we understand, and many other things that I haven't had time to talk about. Then there are the known unknowns, the things we know we don't know. And for example, the rate of expansion of the universe, which is related to the age of the universe. There's lots of observations by different techniques, and they concentrate on two different values that seem to be significantly different. Now, maybe this is just due to observational error, or maybe there's something really fundamental that we don't understand about the expansion of the universe. We know that only 20% of the matter in the universe is stuff that we know about. The other 80% is in dark matter, what we call dark matter. We know about the dark matter because of its gravitational effects, but we can't see it. And there have been lots of experiments, and we don't know the nature of dark matter. And there's also the dark energy that drives the expansion of the universe. There are what's called fast radio bursts, which are very intense but very short-lived flashes of radio emission. Some of the first ones were actually traced to a microwave oven in Australia, but we now understand that most of them originate in distant galaxies. They're very powerful, but by a process that we really don't understand. And then, of course, is there other intelligent life in the universe, or are we alone? So these are the things that we know we don't know. And unfortunately, when astronomers want to get money to build a new radio telescope or any new expensive instrument, they're expected to prepare an extensive scientific justification that describes in great detail how the proposed new telescope is going to answer some, or better yet, even all of these what's called key questions. And if they aren't able to make a convincing argument, then you don't get the money to build a new telescope. And I think actually if the history of radio astronomy is any example, the excitement of the next generation of radio telescopes, such as the next generation VLA, is not going to be in the old questions which they answer, but in the new questions that will be raised by the new observations, the unknown unknowns. So thank you very much for listening. Let me just add, if you're interested in a more detailed history of how radio astronomy changed our universe, much more than I could talk about in an hour, please see our book, Star Noise, Discovering the Radio Universe by Ellen Boughton and myself. You can get a copy from Barnes & Noble or Amazon, and directly from Cambridge University Press, and for a limited time they're giving a discount. Ellen's got flyers outside that let you know how to order the book. So please help yourself on the way out. Thanks again.
Okay, so we'll do some questions. Questions from someone? Yeah, John. Yep.
So Ken, very beautiful talk. You had some, you were sharing some thoughts about the peer review process for getting telescope time. Do you have any thoughts about what could be changed to make it better and ensure that the best science is getting done, or the best, or I guess the best use of telescope time?
Well, yeah. Well, a simple thing, of course, is to build more radio telescopes. And of course, part of the problem is scientists, I guess all professors tend to multiply. Every professor produces a new PhD every few years, and it's worse than the population growth. So when I started out, I knew every radio astronomer in the world. And of course, now there are thousands. And so there are more people that want to do more observing. So maybe we just need population control. Hopefully the peer review process does produce the best science. But I think, as we all know, in a group of proposals, there's maybe 10 or 15% that are obviously better than the others, and there are 10 or 15% that just don't qualify. And that middle group could go either way, depending on who the review committee is.
Questions? Up, Namir? I can probably hear you, man.
Hi, Ken, I really enjoyed that.
Thank you.
Yeah.
Sort of the same question, but why does there have to be such an emphasis on like the killer app and the key questions? Why can't there be more of an emphasis on exploration? In other words, if somebody wants to, well, yeah, that's it. Yeah.
And I think we have met the enemy, and they are us. So one tends to blame the government or the bureaucracy or the NSF for being so conservative. But actually, these proposals are reviewed by other scientists. They're us. But when they're on the other side of the table, they adopt this very conservative attitude of not taking risks. So maybe we all need to change our attitude on this. When you review your next proposal, keep this in mind.
Other questions? Yeah.
Otherwise, on Zoom, they can't hear you.
Yeah, Ken, when I first met you in the 80s, I remember that we were at a conference and you had just used interferometric techniques, Earth rotational aperture synthesis, and had discovered these large masses moving out of jets at velocities exceeding potentially the speed of light. And there was, I remember there was a lot of electricity in the air. Can you describe how you resolved that issue after that conference?
Yeah, it's just an illusion. If things are moving very close to the speed of light toward the observer, the radiating source is nearly catching up with its own radiation. And so two events that occur appear compressed in time. Speed is distance divided by time, and if the time appears arbitrarily short, the speed can appear arbitrarily large. So it's just an illusion. You can work it out with simple algebra. Just draw it out on a piece of paper. You don't even have to understand special relativity.
Other questions? Yep.
Thanks so much for the lovely talk. I'm curious, when we talk about Karl Jansky and his discovery, we hear, oh, he discovered it and then immediately was in the newspaper. But I was wondering if you could shed some more light on how it got into the newspaper. Like, was it Bell Labs? If they didn't seem too excited about it, how did that, story get told to the public?
Yes, that's my understanding, and David can clarify if I have it wrong. But Karl's older brother was a big shot in the electronics and radio industry. He had actually previously worked at Bell Labs. He was very influential. And as soon as he knew about Karl's discovery, my understanding is it was he who convinced Bell Labs to put out a press release. And that's what you saw on the front page of the paper. Is that about right, David? Close enough. It was also Karl's older brother. I didn't have time to go into the history. When Karl originally applied to Bell Labs for a job, he was rejected. And it was his older brother who again had influence and convinced Bell Labs to hire him. Karl had a chronic illness, and at the time the headquarters of Bell Labs was in downtown New York. And because of his illness, they sent Karl out to the sticks of New Jersey. At least it was at the time. And if he had been working in the office in downtown New York, trains and buses and cars, the electrical interference would have been so great he never would have seen the cosmic noise. So it was only because he was originally rejected and his brother got him the job and he was sent out to New Jersey that he was able to have an environment where he could detect the galactic radio noise.
The one over there. Yep.
So Ken, you had some really great descriptions of all of the kind of game-changing, field-changing discoveries in the field. I'm wondering, kind of following up on John's questions, the balance of incremental changes versus game-changing, field-changing kind of discoveries. How do you see that trade-off there in terms of telescopes that we build and the sorts of discoveries that we emphasize in peer review processes and so on, this distinction between kind of incremental changes and game-changing changes? And what do you think would be the best path forward in that trade-off?
Well, I think I said, in modern times, I think all instruments, all scientific instruments, not just telescopes, for example, big accelerators, they're designed to do a specific thing. The accelerator at CERN was designed specifically to detect the Higgs boson, and same thing in astronomy. Whereas in those early years, it was more a matter of being able to build something that was just better than anything that existed, without any particular goal or trying to answer any specific question. Now, whether or not that possibility still exists is, it's not clear. What can we build that's so much better than anything that we have? Well, it's hard, and it's also expensive. Unless you come up with a bright new idea about how to do things. And every so often, somebody does.
Other questions? Okay, well, I think if we're done, I'd like to close by firstly saying that NRAO does not recommend population control to improve the astronomy community. I'd like to thank all of you, and particularly the Janskys, for coming along tonight. It was very special. Many thanks to Lisa and Bruno and Zach and Jeff and others who helped with the production tonight, and thanks to all of you for coming along and making this a very special event. So thank you.
Yeah, I got it.